All right, first we're looking at two graphs that show the same thing. Here's the difference. You ready? Look at the x-axis. In the first one, they're saying let 1970 be x equals 0. And in the second one, they're saying, well, let 1970 be 1970. So that's the difference. Everything else mathematically is pretty much the same. And we're going to talk about how those differences are impacted in the equation. So first question, interpret the slope of the linear model. Okay, well you can see the slope is the same in both of them. So our slope is 0.016344. And slope is always a fraction, so we put that over 1. The top represents the y values. The y values are degrees Celsius. And the x values are years since 1970. So we can see, now our slope is positive, so we can say that the degrees in Celsius increased 0.016344 for every year since 1970. Let me go ahead and type that out. And there you can see the sentence in red at the bottom. The degrees in Celsius have increased 0.016344 for every year since 1970. And that is what our slope means. What does x represent in each of the graphs? Well, we kind of already talked about this, but it's years since 1970. Right? That's our x-axis. Use the trendline equation from this first graph to predict the average global temperature in 2016, rounded to the nearest hundredth. Now, remember that in this one, 1970 means x equals 0. So 2016, well, how many years later is that? 46. So we're going to use an x value of 46. So y equals 0.016344 times 46 plus 13.963768. Lots of numbers there. All right, we went out really far in the decimals, which is good. It's more accurate. A little accuracy never hurt anybody. So remember, we're going to multiply and then add. We end up with a y value of 14 72 hundredths. All right, so 14.72 degrees Celsius is what we would estimate using this particular model. Now, on this one, now we're using the other graph where 1970 is 1970. So now let's predict for 2016. So now we're just using x is 2016. So let's plug that in to the same, well, to this equation, right? We're using a new graph, so it's a slightly different equation. Look how we subtract the y-intercept instead of adding in this particular case. So we multiply first and then we subtract, but notice you still end up with 14 72 hundredths. Same exact thing. So even though we are dealing with two different equations, because our x values are different, it changes our equations, we still end up with the same answer. So this shows that, you know, your y-intercepts are going to be created dependent upon how you're dealing with your x-axis. And the last question, what is the dependent variable? Well, the dependent variable here is degrees Celsius, right? Degrees Celsius. Would it make sense to reverse these? The answer to that is no. Right now, we can say that the degrees Celsius depend on the year, right? As the years get closer to the current, right, closer to 2018, our degrees Celsius increase. It would not make sense to say the year depends on the degree. You can't say it was 12 degrees Celsius and say, oh, that must have been 1962. Right? That's not necessarily how it goes because multiple years might have the same temperature. So the degrees have to depend on the time. That's just what makes sense.